So you should all be able to see the first sheet now. Today I'm going to learn you something, hopefully a bit more about slurry analysis and shell material test methods. Shortly, and not everybody from you might know me, so I would like to introduce myself shortly. So my name is Carel Wegman. I'm 38 years old and I'm based in the Netherlands. And prior to joining the team at R&R, I worked about 10 years as a production engineer and quality manager at Eurocast in the Netherlands. There is also a Eurocast in Tunisia, so don't mix it up. Eurocast was a investment foundry casting aluminium and steel for the aerospace and the defense industry, using both plaster block molds and, of course, the shell process. In 2011, I joined the team at R&R, where I give technical support to all of our customers in Northern Europe, the UK, and Israel. And I really focus on improving our customers' shell performance, the cost, quality, production efficiency, and also give on-site training and support to the shell room engineers. So the subjects for today that we go through, well, you know, many of you might already be familiar with our company. I thought it would be a good idea to give you some background information about who we are and what we do. With regards to slurry analysis, I want to explain why it is so important to perform by giving some background information on colloidal silicas and to go through the practical test procedures. And I'll also try to explain, you know, how corrections should be implemented. At the end of the presentation, I will explain what shell material test methods are nowadays available and how these can help you to improve shell-related issues. I hope to cover this all within the set 45 minutes, but at the end there will be time for questions if needed. So regarding R&R, we were originally founded in 1872, which is actually make us a, well, I would say, well-established supplier in our industry. Originally, we provided actually furniture for barbers, dentists, and doctors. But in the 1900s, our focus changed as we developed new products for casting applications. This included, you know, different investment materials for the dental and the jewelry production, including the development of the first vacuum casting appliance, actually. But at the time of World War II, we developed industrial solid mold materials to produce castings. And later on, we developed, you know, water-based binders like Prime Coat and Deluxe Coat, which are actually binders which are still successfully used in many foundries. In '64, R&R was purchased by a company called Dentsply Sirona, and Dentsply is a supplier of innovative dental products, and they are NASDAQ registered under X-ray. At this time, we also started to distribute ceramic shell materials all over the world. But we're still serving the four markets that we, you know, originally started with, which is quite a unique, actually. Because we think it's, you know, it's really important to promote value through a solution-based approach. I think it's, you know, very important to have a strong relation with foundry management, but also with the production engineers. I always try to get, you know, really familiar and get every detail of our customers' processes and shell rooms, being able to understand, you know, the details when there are issues and when help is needed. You know, by giving this, you know, pragmatic technical support during, you know, the development, establishment, but also the conservation of a shell system, we're able to supply, you know, tailor-made solutions which are specific to your requirements. Today, R&R offers a complete line of ceramic shell products, and these include high-performance systems like primary and backup binders, refractories which can be blended according to specific needs if that is required. We also have a range of core materials which can be applied directly against the wax pattern or into shell cavities, or, you know, they can be used to preform them in a tube that can be used, you know, during the wax injection. We also have shell consumables like stuccos and pouring cups, slurry additives, wetting agents, anti-foam, of course, but also drying indicators. We'll support, as I said, the lost wax mold casting materials like plasters and investments, and these can be used for different applications. But in this presentation, I'm not going too much into detail about these things, but if you have any questions around this, because it's very interesting, then you can always contact me. But I think what is most important to mention is that R&R is able to customize ceramic shell systems specific to your requirements or a foundry. So let's start to talk about slurry analysis as the controls. Why should I perform slurry control? Well, this is maybe quite an extreme example, but it surely gives you an idea what can happen to a slurry when it is not prepared well, or when it's not controlled well. I mean, obviously something went quite seriously wrong here. I mean, you need to understand that a slurry formulation is chosen for a very specific reason. I mean, often we make a unique formulation for a foundry, and these formulations they consist of course the binder, which is SiO2 and water, refractories, the polymers, effectants. In some cases we add fibers to a slurry, etc. I mean, the behavior and the characteristics are of course a key element to produce successful castings, and we need to maintain these ratios for the slurry to behave properly, because in the end, good formulation with bad preparation and bad controls will give bad cast results. So a number of relatively simple tests were developed over time that can be performed by actually any user of ceramic slurries. And in the presentation, we will go through the procedures and the backgrounds as they are listed here. And it should help you to understand better, why are these performed and also how these are performed. But not every foundry has currently the resources or the equipment in place to perform slurry analysis. So R&R has the possibility to perform all of these tests for you at our lab in the US or in the Netherlands. And we can supply you these kind of insulated bottles to protect them against freezing. If you think that that you need some support from us to do these tests. Well, the goals of slurry control are three. I mean, you want to maintain the binder stability by measuring the binder solids and the binder pH, but also the slurry temperature. We want to maintain slurry and coating integrity by measuring the viscosity of the slurry and the density. And you want to maintain, of course, optimum shell performance. This again requires the binder solids measurements, refractory solids, but you also want to consider an MOR or stress strain analysis, including the permeability of the shell. But first, before we start talking about the practical aspects, I want to explain a basic description about colloidal silicas, because there's a lot going on inside these binders, making slurry control so important. I mean, colloidal silica is produced by suspending microfine particles in water. And you need to understand that each of this colloidal silica particle is surrounded by an ion to give it a negative charge on the surface. And the charge around each particle maintains, a suspension because they are repelling one and another. You could compare this actually by holding two magnets against each other with the negative poles, and you will notice this repelling effect. So imagine that this is happening with every silica particle in water. The repelling effect will keep them in suspension. Typical concentration of colloidal silicas are 20 to 30%, and the diameter is somewhere between 2 and 100 millimicron. I mean, higher concentrations are, of course, available, for example, with our EHT binder, which is used in extreme high temperature aerospace applications. It was developed in the first place for single crystal castings, but it can also be used in other extreme applications. There are different ways to stabilize a colloidal with this negative charge around the particle. The most common is the use of the alkaline sodium hydroxide ion, which gives a very good stability of the colloidal when the pH is kept between 9 and 10. The particle size of the colloidal is on influence of the stability too, because a small particle of 8 to 10 nanometers comes, of course, with a greater surface area. So it therefore requires a higher level of sodium hydroxide to stabilize it than a large particle, which is between 14 and 15 nanometers. So you need to understand that the surface to volume ratio is quite crucial here. The same concentration, a larger particle of colloidal will therefore, be more stable than a smaller particle. So R&I used this knowledge to improve slurry life performance, although our prime cut binder, which is considered a small particle, was already performing really well. We developed Prime Cut Plus, which is a large particle binder, and that showed improved slurry life, even when it is used in combination with, for example, a cobalt aluminate nucleator. Alternatively, a colloid can be stabilized using a charged aluminate ion. This is a very high surface charged ion that makes the binder even stable in an acidic environment of pH 4 to 7. It takes all the concerns away regarding slurry life, and they are actually quite ideal for prime slurries. It's typically not used for a backup binder because it has a lower green strength. But I've already mentioned 3 different types of stabilization, and each binder comes with specific characteristics and behavior in production. So it's very important to consult and think, what is the right solution for me? This is something that we can help you with. So now you understand how a colloidal silica is stabilized. I mean, it's very interesting to understand, what happens when it is destabilized. And there are 2 main reasons. The first one is the alteration of the particle charge around the silica particles. And the other one is an increase of the concentration of the particles, which could promote particle collisions. I mean, both of these results, and that's very important for agglomeration or gelation of the SiO2, which is irreversible. It's irreversible damage to the binder. So it's really important that we perform slurry analysis to prevent these issues. So let's start explaining a bit further the first reason, the change of the particle charge. So we already learned that the negative charge around each particle prevents them from coming in contact with each other. So if I would introduce, for example, unwanted positive ions, this protective charge will be reduced. Once the charges are reduced sufficiently, the silica particles will no longer repel each other. They will start to polymerize and start to create change. And this is reducing, of course, the surface area and the number of particles available for bonding. So the larger this change gets, the lower your bonding strength of the binder will be, and in the end, the binder will start to gel. So how could we prevent this gelling of the binder by the particle charge? I think bacteria and mold infections in the slurry are quite a common reason, because these microorganisms emit a low pH substance. It does have a detrimental effect on the colloidal stability. So to prevent these infections, general housekeeping and social hygiene is actually quite important in the shell room. Although I think there's a lot of common sense here to prevent these, as long as you are actually aware of it. But common sources are, for example, buckets with filthy water or water residues in mixers and pumps. We all know that we need to use deionized water in the shell room to prevent the introduction of unwanted ions. Therefore, I think it's very recommendable to check your deionized water regularly on this conductivity, and it can be done quite easily with meters like these. The maximum conductivity of deionized water should be 5 microsiemens, and to prevent growth of microorganisms in your deionized water, I recommend to store your water in opaque containers. But I have to say, I want to prevent that I start talking for another hour about the importance of water quality alone. I'll suggest that you take a look at our website and download one of our latest technical tip sheets about purified water for slurries and their control. It gives a lot of background information on this important subject. A remarkable reason, actually, for the alteration of the particle charge are the refractories that we add. And especially zircon has a detrimental effect because it has a relatively low pH, and we prefer with alkaline binders to be around pH 9 to 10, which is high. And zircon has a very high concentration in the prime slurry. Also because a prime slurry is not used and replenished as much as a backup slurry, it is very important to use a refractory with a proven quality and is applicable with the binder that is used. Nowadays, zircon is offered by many different suppliers in different price categories, but it also means that the quality between them does differ between the available sources. So to prevent slurry life issues, I always recommend to check your zircon on trace elements like, for example, iron oxide. Depending on your slurry turnover, a high contact can have an impact on slurry life. So next to the particle charge, an increase of the particle concentration could be a reason for binder instability and gelling. Because while a slurry is in motion, it evaporates water, but it also absorbs actually water. And it's a reason to control the viscosity and make corrections when this is needed. And when the corrections on the viscosity and the binder solids are not made consistently, too much water will evaporate, which increases the concentration of the particles in the binder. And that in the end could result or could promote actually particle collisions, forming these change in the colloidal. And in the worst case, it will make it gel. So to prevent these kind of issues, it's very important to control the binder density and the viscosity. And the two pictures here shows a sample which is liquid, of course, on the left, and the yellow one is completely gelled after a gel test. Yellow has nothing to do with the test. That's just a binder sample with our drying indicator. That was a nice example to show. So now there is a beautiful aspect that occurs during the destabilization of a colloidal, because while the particle charge starts to agglomerate due to the alteration of the particle charge or the increase of the concentration, the pH is dropping too. So this is making the pH a very important test to perform to control your binder stability. Because once the binder is irreversibly damaged, it's irreversible, and you need to replace the slurry. And replacing the slurry is already expensive, but at that point you will probably also see a lot of cast quality issues, which is, I think, maybe in some cases even more expensive than replacing a slurry tank. So I think it's highly recommendable to invest once in the required equipment and the work area to perform slurry analysis in, because this will prevent major issues with slurry and shell quality. And slurry analysis must be encouraged with good quality materials, training, and give people the time to do this, because it will pay back. So now we come to a more practical phase of the presentation, how to perform these tests. And we start with the binder density. So being able to measure the binder density, we have to separate the binder from a slurry with a centrifuge. And normally samples are centrifuged. We normally do it 2 times at 30 minutes at 4,000 RPM in tubes like these. But before I continue with measuring the actual binder density, I want to point out the importance of this sample preparation, because the centrifuge binder is used at multiple tests, so you need to have enough material available to do them all. I normally prefer to have at least 40 milliliters. And to do that, I always prefer to take a sample of the slurry a few hours or the night before and already let the refractory settle by gravity. This makes it much easier to get a large volume of this binder. Of course, you can take samples directly out of the slurry tank if this is needed, but it takes more effort and time to spin the binder out. The quality of this preparation and this binder is very important on the test reliability. So good preparation, good equipment is very important here. And I can speak from experience that, performing slurry analysis on a weekly basis. I mean, I've been doing this for almost 10 years. It's not the most exciting job to do. But if the required equipment, training, and the time is supplied to the operators, it will encourage them to do it, and you will see improved slurry stability and cast quality, of course. So the purpose of measuring the binder density is to control, of course, the level of the SiO2 in the binder, and there are different methods to do this. Very common one is the use of this 10 milliliter flask, which is used in combination with an accurate scale. And these scales can be really simple. Something like this is already working, and it's a cheap way of doing this actually, but there is a drawback because it's quite sensitive for human errors due to the visual interpretation of the liquid phase against a really fine line in the flask. It's often quite difficult to see where the meniscus is exactly placed because of the surface tension of binder and the collar. I think what is actually a better method is the use of a pycnometer. And the pycnometer works very similar as the 10 milliliter flask. I mean, you fill it with binder, you put the cap back on, everything which is too much is flowing out. So the whole visual interpretation is taken out of the equation. Drawback, I think these are actually quite expensive. They go up to 80 euros per flask, and they break, they have to be replaced. So not sure. If you want to do it right, I would choose one of the electronic density meters. I mean, we've been using these for a long time on our lab now, and they are foolproof. They take all the risk from human failure out of the equation because binder is injected in it, and it just shows you the density of the binder with 4 digits behind the 0. This one works with a Bluetooth device, and it's actually quite affordable. If you do decide to use, the volumetric flask like the pycnometer, I recommend to have enough available to cover each sample. Otherwise, the operator has to clean and dry the flask in between measurements. It's a hassle. You don't want that. If you do use the flask, I also suggest you take a look at one of our latest technical tip sheets, flask calibration and use, because often I see on the shop floor that mistakes are made here. They're not filled right or they're not calibrated, which is very important. So this technical tip sheet is explaining to you how to use and calibrate this flask correctly. So it's available, it's free, please take a look to it. So pH measurement. The purpose is, of course, to determine the colloidal stability, because when it is destabilized, the pH was dropping. First, I want to note that it's very important to calibrate your pH equipment. I always prefer to use these kind of solutions. In case of an alkaline binder, you need to calibrate your equipment with a pH buffer 7 and a buffer 10. In case of an acidic pH, it's buffer 4 and 7. So it depends on the specific binder, what specification you need to follow. But normally with the alkaline binder, anything above 9.5 is considered good. When the pH is too low, so for example, it drops under 9.5, it's going to 9.2. It is possible to stabilize a colloidal silica with a, for example, 1% ammonium hydroxide solution. But I have to admit, I'm not a big fan of it. Not at all, because this correction, I see it as a delay of execution, actually. It should be prevented that your binder pH is dropping. So once you have experienced issues with your pH, it's so much more important to find the root cause and eliminate it. If you don't do this, it will come back. So some technical tips for accurate pH measurement. Make sure that you always dry and pre-rinse the electrode in an actual sample container, so you prevent that the actual sample is contaminated from one to the other. And always store your pH meter in a dedicated storage solution. But if you do not have this, don't store it in deionized water, because deionized water has no ions in it, and it will withdraw the ions in the liquid of your pH meter, and it will reduce the lifespan of your pH meter drastically and cause wrong measurements. So as explained, the pH of a slurry can be affected by poor water quality, or refractories, pattern cleaner residues, or high binder solids and bacteria. But also low slurry turnover is often the case of slurry life and pH issues. I mean, when I see a showroom and production is really slow, I strongly recommend to keep the volume of a slurry tank as low as reasonably possible to encourage fresh material is added to it to improve slurry life. If bacteria is found in the slurry, I mean, we don't recommend to use bleach. It will have a detrimental effect on the colloidal stability. So we recommend to use a bactericide which is applicable with the binder used. And we have Grotan, which comes with specific instructions based on the number of counts on the test strips. And the test strips that we always use are like these. And this is really simple. Again, you need the centrifuge binder, which need to be really clean, because if there's any residue of the refractory present in it, and it will cover it and it will make it more difficult to read it off. I have the best experience with these EICF combi test strips, because they can test both bacteria and fungi in quite a reliable manner. So explain that. Slurry temperature. Why should I measure it? Well, it's in the first place quite an easy test to do, and it reduces the risk of rapid evaporation causing viscosity issues, but more important, high binder solids. It will also help to reduce, of course, the risk of bacteria growth in your slurry, because bacteria really like it to grow in a warm and moist environment. So normally we recommend to keep the slurry somewhere around the same temperature as the room temperature, but never higher as 28 degrees C. And often I see, slurry temperature issues caused by equipment. And you need to think also of radiation heat of the motor or the gearbox or failing air conditioning units. If you still have some issues with the temperature, you can consider adjustments of the RPM or even the blade. And this still doesn't help. A chiller might be required, although I would prefer to prevent this, just like changing the slurry recipe to prevent temperature increases. Slurry viscosity, very important. But on June the 30th, my colleague Bastian Schulte will present a very detailed presentation about viscosity measurements. And the paper where this is based on, a comprehensive analysis of viscosity measurements, is available for our site. It can be requested. Because of this, I won't go too much into detail about viscosity measurements, but because it is maybe the most important test that we can perform at a slurry tank, I do need to point out a few things. I mean, obviously, the purpose is to measure the flow and coating properties of a slurry, and the test is done really simple. We all know this. You put it in the slurry, and once you take it out, the slurry starts to flow. You start the time, and then we need to stop somewhere. And there are different methods people choose from. There is the 1 inch below the cup. So when the flow is interrupted 1 inch below, people stop or break at the bottom. If you do decide to use one of these two methods, please make sure you always work at eye level, because a change of the angle will change the visual interpretation of the 1 inch below the cup, for example. So I think what is actually a more reliable manner is to through the hole. So you look inside the cup and you wait till it opens up. But honestly, I don't care how you do it. I don't care what cup you use. I don't care if you do it upside down, as long as you do it consistent every time by every operator. Because this is often quite the case that I see that operators they measure not always the same thing. And if one operator is measuring 1 second higher compared to the other, he will make a correction while the other is not. And this can cause, fluctuations in the binder solids. Another thing I want to point out is, the importance to keep your viscosity cups clean. The smallest buildup, like the one on the left, is actually quite a big buildup, but even a small buildup can already cause a 1 to 2 second deviation. If you consider that, the viscosity specification is often plus or minus 1 second, that can be a big issue. What I don't like it as a technical engineer is that I'm called by a foundry saying we've got shell-related issues and cracking shells, and first thing I always do is to check the viscosity cup, and you don't want to believe how often it's just a dirty cup. Slurry density, it measures the combined density of all the components in a slurry. So it is a fitness for use test. But this test is also for me important because I need a value to being able to calculate the required slurry correction. I'm coming back on this. It works very similar as with the binder density, but now we use a 100 milliliter cylinder. Don't forget to check these cylinders too. They say they're 100 milliliter, but it's not really exactly 100 milliliters, so it's good to check, and it makes some difference. Also, R&I has a YouTube channel where we made some different videos, and one is regarding the slurry density. So if you take a look here, it will tell you in detail how to perform this test. Might help you. We'll also have some instructions on how to use our slurry control worksheets, etc. So this test is very helpful to have a general impression of the slurry condition. But if it is out of spec, you can of course have issues with, for example, weak or too strong shells. But at this case, you want to know more. If it's out of spec, what is the ratio of refractory and the binder solids in a slurry? So therefore, you really should perform actually also a total or refractory solids test. And it is, the purpose is to determine the actual percentage of refractory in slurry by measuring the total solids. And this test is really simple. You take an aluminium drying pan, it's empty, you fill it with some slurry, you dry it for an hour at 180 degrees C, and you weigh it again. Really simple, very straightforward. If you want to do it more quick and easier, you use a moisture balance. Works the same way, but the equipment is doing the calculations for you. And then after some calculations using both the binder solids and the refractory solids, you can determine how much refractory is actually in my slurry. It's very helpful because if the results are high, you can have issues with brittle shells actually. And they will crack at the D-wax. If they're very high, you can also have hot tear defects in your castings or permeability issues like non-fill and gas. When the refractory solids are low, you can have issues with weak shells, and they will crack at the boiler clave or at de-waxing and at firing. But also you can have leaks and runouts. But also shell bulging is an important reason for low refractory loadings. The gel test. Well, it's the purpose of the gel test is to determine actually the stability or the thickness of the binder. It's an easy test because we just take some binder which we have centrifuged and we place it in the oven at 60 degrees C, and we're going to check after 24 hours if the viscosity has increased. I always compare this test with like some sort of crystal ball. You can look a few weeks ahead to see if the binder is going to cause you any issues. If it is in really bad condition due to the particle charge alteration or a high concentration, it will during the test thicken up or maybe even completely gel. I had to sabotage a sample to show you a gelled binder because I don't see that very often. But if it does happen within 24 hours, you must discard the slurry immediately because at this stage we'll already probably start to see some serious cast issues with spalling or leaks, etc. If the test is positive, within 48 to 72 hours, you have a bit more time to schedule in a replacement. But in any case, it's bad news. I just want to point out the 60 degrees C, that needs to be quite accurate. You can't really perform this test in a reliable way using an average pizza oven. It needs to be a laboratory grade style of oven. This is sometimes people holding away of doing this. So now we've discussed all the tests. The question comes, how often do I need to perform slurry analysis? And this is a table I normally leave my customers with that explains exactly, what the slurry should look like, what are the specifications, test frequency, etc. The frequency of testing is actually depending on the stability of the weekly test results. If you struggle to keep your slurry within specification, more frequent testing is required. By performing, regular slurry analysis, you will start to learn and understand how the slurry behaves and what correction is required during the week. Once the slurry is considered stable, a reduction of the frequency, can be considered. But I would always stick with at least once per week. The use of a slurry analysis data log, where you put in the results but also the added corrections, is quite essential in this case. You might note that I make a difference between fixed and secondary parameters. And for me, a fixed limit means that, you need to respect the specification at all time. A secondary limit means that the target value can be adjusted over time within its limits, of course. So in this case, for example, the refractory loading and the slurry density are actually in function of the slurry viscosity. I will explain this a little bit further. This table is a basic correction guideline based on viscosity and binder solids, and it can actually be used on any slurry, because whereas the binder solids and the viscosity cover a broad and important performance aspect of the slurry, I already see quite good results when I finally decide to steer on these two characteristics alone. But when cost quality issues come to light, you want to have more in-depth results, including the refractory loading. Now we have developed binder-specific slurry control worksheets, and the found results like the weight of the drying pan and the volumetric flask, they are simply put in there, and the sheet will calculate what is needed to bring a slurry back into its set specifications, which is mentioned here in green. The volume of the correction is calculated according to the volume of the slurry present in the tank, and therefore we also need the slurry density, being able to calculate this. Although I think these sheets are fantastic and they're great and they put you in the right direction, they're still a little theoretical, because there is an aspect that this sheet doesn't know. It can't take in consideration the viscosity of a slurry at that specific moment. So therefore, the operator needs to understand that the refractory loading its target value might have to be adjusted over time within its limits, being able to make a correction to the viscosity. Over time, we see that the refractory loading of a long-lasting slurry slowly increases, while the viscosity is always kept at its target value. So try to explain why this is. Because it has to do with the continuous motion of the slurry in tanks to keep it in suspension. During this motion, the refractory particles, they wear and they round off. This is reducing the viscosity. And the increase of the refractory loading at that time is sometimes required, to keep the viscosity at the same level. At the same time, water is evaporating, which is increasing the binder solids, but also the viscosity again. So therefore, you might have noticed in practice that, while the viscosity is kept, within its specification by adding water, the binder solids still tend to rise out of specification. So it means that when the slurry is aging and it wears over time, more water and refractory is needed than necessary for viscosity corrections alone. So in practice, I recommend foundries to prepare a couple of times per week a small top-up recipe where binder ingredients are replaced for deionized water. It will help to reduce the impact of this phenomena, and it keeps the binder solids within specification, which is so important for consistent performance. So now it's better to make several small corrections per week than one big correction once in a while to prevent fluctuations of the slurry characteristics. So now we're going to talk a bit shortly about shell material test methods, because there are many reasons for a foundry to consider testing its shell characteristics. And common reasons are found, of course, in casting defects related to the primary layer, but more common nowadays is the desire to improve the backup slurry's performance. Think of issues with shell cracking, non-fill bulging, but also the desire to improve production efficiency by reducing dry time or coats. So we have an advanced product application and development laboratory, including a research foundry with a boilerclave and an inductive filter. Through the following sheets, I want to explain what test methods are available and how this can be beneficial during the development of a new system. I mean, common and renowned measurements are, of course, MOR, which is used with these kind of wax bars, which are shelled. And MOR measures the maximum stress at fracture of a test piece. And this test is beneficial because it will tell you at which point the shell starts to crack. We are able to perform these tests at the actual temperature of the casting. AFL is very similar to MOR, but it measures the actual load bearing capacity and is depending on the thickness of the shell. But we also developed a stress strain analysis, where MOR looks at the maximum stress on the shell when it breaks. Stress strain analysis tells you something about the flexibility of the shell system. And the graph is an example. You see two different shell systems, and they both have the maximum stress, but the sample in yellow can actually absorb a lot more stress because it's expressed over more flexibility. Permeability is, of course, a very known test, and it can be performed by using, the well-known ping-pong ball method. A ping-pong ball is glued against a ceramic tube and it is shelled. After that, it is fired, so the ping-pong ball burns out. And then we're going to, compress air through it, and it helps you to understand how gas is traveling through the shell, and it can help you to reduce, non-fill or gas defects. This is also a test that we can perform at temperature. Also, what is very interesting, I think, is that we are able to measure the green permeability of a shell sample with the equipment displayed completely on the right. It measures the ability of wax to penetrate the shell during de-waxing. And if you have a shell that's, of course, permeable in green condition, it can lead to, reduced shell cracking because you reduce some of the stress that is applied on the shell during the de-waxing process. And in line with this green permeability, R&R developed the scrap test, and it measures the shell's capacity to resist autoclave pressure. And the setup is quite pragmatic and simple, actually. We set up a tree with these small wax spheres, and if needed, we can supply you, the tool so you can use your own wax, because that obviously has some influence here. Instead of wax sprues, we use a screw, a metal screw, and then the tree is going to be shelled. So during de-wax, the wax sphere cannot drain through a sprue, so it will generate maximum expansion force inside the shell. And once de-waxed, we can compare, different shell systems based on the cracks. And using this method, I have developed a shell system, for example, for foundries, where we were able to eliminate shell cracking. And I used a fiber-based shell system, which was quite remarkable, that when the spheres came out of the boilerclave, the fiber in that system was completely covered in wax. So first you thought, oh, it's cracked, but then you take a look to it, there's not a single crack in it. The shell is so permeable that all the wax actually went straight through the shell. So this also resolved quite some issues with non-fill defects and cracks, and we were able to reduce a coat. So it's a very interesting test which can be implemented anywhere, actually. Another test that we developed is the spalling load measurement. It's developed to help overcome major spalling issues one day at a foundry in the USA. And this video I will walk you through the spool test process. And we use a no stretch fishing line, and it's attached to the force meter, and the sample is connected to the meter with a unique self-made T button. The table and sample are leveled, and then some force is applied to the sample, and then we measure the maximum force, and that's a measure for the spool load. The spool load test measures the intercoat adhesion between ceramic shell layers, and we can use this info to optimize slurry and shell building parameters, resulting spooling defects. And data showed that when more force is applied to pull off this button from a sample, spool defects in practice reduce. And we can perform these tests on the same flat bars like MOR samples. Other specific measurement techniques are available to understand the characteristics of raw materials, like thermal expansion dilatometers are used to analyze how ceramics behave at different temperature ranges, as well as how they expand and contract. So this can be quite important to understand issues with dimensions of castings, etc. And a particle size analysis is a technique that can be used to understand coating characteristics or strength and permeability of shells. So there's a lot available. And this, I think I'm also running out of time now. This completes my presentation on slurry analysis and the shell material testing. And I really hope that it was learnful. And what I hope that I've tried to achieve is that you are encouraged to take a look at your system controls and characteristics, and be more in control. And if you feel that we can help you, you can always contact me afterwards.